All right. I wanted to talk a little bit about why this idea of electron configurations and orbital diagrams helps us to understand certain things. At the start of the school year, I told you that group one elements, lithium, sodium, potassium, would get a +1 charge. And I told you that group two elements get a +2 charge. And I told you that without giving you any reason why. And then as we go to the other side of the periodic table, I said things like nitrogen gets a -3 charge, oxygen gets a -2 charge, and things in the oxygen group, and the halogens, fluorine, chlorine, bromine, and iodine, get -1 charges. And we can justify that. And I'm not going to go through, the whole periodic table here, but I just want to show you a couple of orbital diagrams as to why this is the case. So let's just take a look at for example, sodium. Sodium, if you were going to draw the box diagram, we'd have, hang on, I already screwed it up. The 1s orbital, 2s, 2p, and 3s. So if I'm going to fill the electrons, I have 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, atoms would like to have a completely filled outer shell. So what's going to happen here is if sodium loses that one electron, then it's going to have the electronic configuration of neon, a noble gas configuration, a full octet, we call this. These are the valence electrons, and we have 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons in the valence shell. That's called an octet. And atoms will either lose or gain electrons in order to have that octet. Same thing with beryllium. If we look at beryllium, it has 2 electrons there. It wants to have 8 electrons in its valence shell. So it's going to lose 2 electrons. I mean, it's a lot easier than gaining 6 electrons. Where are you going to put them, right? There's only so much room around that atom, and electrons will repel each other. So we're going to get to a case where we lose those 2 electrons, and something like magnesium is going to get a +2 charge. Now let's take a trip to the other end of the periodic table. Things like nitrogen, oxygen, etc. Taking a look at nitrogen, we have the 1s orbital, the 2s orbital, and the 2p orbital. So for nitrogen, we're going to go, we have 7 electrons, 1, 2, 3, 4, 5, 6, 7. Okay. And I told you, hey, nitrogen, when it forms nitride, it gets a -3 charge. Well, remember, we want a full octet. So we're going to get 1, 2, 3. We're able to accept 3 electrons, and that accounts for the -3 charge. Take a look at oxygen. Oxygen has 8 electrons, 2, 4, 5, 6, 7, 8. And in order for the valence shell to have the full octet, you'd have to gain 2 electrons, and that accounts for the -2 charge. So this is why I told you at the beginning of the year, just learn the charges these things get, and I told you I'd explain it later on. Fluorine. It needs 1 electron to complete its octet. So as we move from group 1 and 2, the alkali metals and the alkaline earth metals, they're going to be losing electrons. But as we go over to the nitrogen group, the oxygen group, and the halogens, they'll be gaining electrons. And one of the reasons that I talk about the noble gases as being inert or non-reactive is because, look, there's neon. It already has a full 8 electrons, a full octet. Doesn't need to gain or lose any electrons. So just a little rationale for the charges that you see on the periodic table and on these ions. Now, of course, in next chapter, we're going to be learning about covalent molecules and how atomic orbitals form molecular orbitals, and we can account for certain properties of molecules. So, do you guys have any questions at all for me on the worksheet?
Maybe 17.
17? Yeah. Okay. 17 says, what are the possible angular momentum, magnetic, and electron spin quantum numbers associated in the s orbital of n equal 3? So when you first read that, if you're not used to this type of jargon, it kind of sounds like word salad. But immediately, when you look at this, you got to pick out some key things here. We have n equal 3. That means the principal quantum number is 3. The energy level is 3, and it says an s orbital. So the s orbital, we learned that the s orbital only has one orbital in the set of s orbitals. This would be the 3s orbital. And the L value was the angular momentum quantum number. For s orbitals, that has to equal 0. And the m sub L, the magnetic angular momentum quantum number, would also have to equal 0. And then, of course, your spin, your m sub s, if I have one electron, I would say plus 1/2. Okay. One of the things that you should remember, and if you want to write this down in your notes page, or anyone else for that matter, let's make sure you have this stuff. Let me kind of go through it one more time, as many times as we need to. Our n level, it goes from 1, 2, all the way up to actually, you go up to infinity. But for each of the n levels, you're going to have different numbers of angular momentum quantum numbers. So for the n equal 1, our L values go from n minus 1, they start at 0 and go up to n minus 1. Well, if n is equal to 1, well, we only have one option here for our L value. N minus 1 is 0. So for n equal to 1, we only have L value of equal to 0. So we can only have s orbitals in that. So remember, L equals 0. Those are s orbitals. And that could be I can have a 1s orbital, a 2s orbital, a 3s orbital. But you'll see as we move to higher levels, like n equal 2, for example, my allowed angular momentum quantum numbers would be 0 and up to n minus 1. 2 minus 1 is 1. So these are the allowed values for my L values. Anna.
What does the L stand for again?
That's the angular momentum quantum number. And angular momentum, for right now, we can just think of that as causing a little higher energy for those orbitals. Okay, I don't want to get into that too much, and it's really interesting, but it's kind of crazy to think about. So let's just understand and remember, for the sake of this course, that if I have L equal to 1, those are the p orbitals. P orbitals. Okay, and the m sub L values you get is equal to 2L plus 1. So whatever my L value is, this is the magnetic angular momentum quantum number. And what that tells us is, I'm going to have 3 orientations in space. And for example, for the L equal 1, I have 2 times 1 is 1, or 2 times 1 is 2, plus 1 is 3. So I'm going to have 3 possible orbitals for L equals 1. And these are called the p orbitals. Now, so we could say, well, what are these values for m sub L? Well, it's going to be -1, 0, and +1. You know, I'm not too concerned that you know that. But actually, these three p orbitals are oriented in space in such a way that they align along the x, y, and z axis. So when I have a set of p orbitals, I have a px, a py, and a pz, and they do fall along the x, y, and z axis, x, y, and z. So the pz orbital would be shaped something like this, kind of like a dumbbell right along the z-axis. The px orbital comes out of the plane at us and looks like that, and the py orbital is along the y-axis and looks kind of like that. And again, you could look at the art on the wall back there with the orbitals. So if I'm talking about the n equal to 3 level, well, then we've got s orbitals, we've got p orbitals, and we also have something called d orbitals. The d orbitals have an L value of 2. And 2L plus 1, I've got 5 possible d orbitals, or 5 d orbitals in the set. And they're oriented. I'm not going to try to draw them, but they're oriented just like the picture on the wall back there if you want to take a look at them. So, to summarize, put a chart like this in your notes. Okay. For my principal quantum number, n equal 1, possible L values, 0, 0 and 1, 0, 1 and 2, 0, 1, 2, and 3. Okay? Orbital type. S, S and P, S, P, and D, S, P, D, and F. M sub L values, 0. For an s orbital, you only have 1. 0, and then over here we have the m sub L values. We have -1, 0, and +1. These are just designations that we're going to use for it. Don't worry about the significance of the -1, 0, and +1. Those are just labels for them. Again, over here, s orbital 0, the p orbitals -1, 0, +1, and for the d orbitals -2, -1, 0, +1, and +2. These are just representations of how we label the d orbital. Well, the quantum numbers for the d orbitals, but they in fact have different names. The d orbitals have names. I'll write them down. We have dxy, d xz, dyz, d x squared minus y squared, and dz squared. These are just names for these things. I don't care that I'm more interested in you just understanding that I've got 5 d orbitals in the set. But I want to just kind of be complete and say, this is, the story that you're going to encounter if you pursue this. And finally, for f orbitals, we're going to have 7 of them. And quite frankly, I'm not going to write the names down. I'm not going to try to show you the shapes. We're not going to deal with f orbitals too much, except if we're writing electron configurations. Anna?
So if you're given a thing and it has an L that equals 0, it could be 1, 2, 3, or 4. How do you know?
If L is equal to 0, then it's an s orbital. It doesn't matter what n level it's in.
What about the has less than 0, 1, 2?
Yep, these are the possible L values that you can have. So in the 4th energy level, we can have s orbitals, p orbitals, d orbitals, and f orbitals.
Okay.
And when we split these into the m sub L values, that gives us the number of orbitals per set. Okay. So to kind of wrap this up, s orbitals, no matter what energy level I'm in, there's only one s orbital. The 1s orbital, the 2s orbital, the 3s orbital, and they hold a maximum of 2 electrons, the s orbitals. The p orbitals you don't see until you get to n equal 2. And when you get to n equal 2, then you have the 2s orbital and the 2p orbitals that come in a set of 3. So you can hold a maximum of 6 electrons in those 3 orbitals. But they have to have opposite spins. D orbitals, I have 5 of them, maximum of 10 electrons they can hold, and that's pretty much it. So I think that's it for the chapter. Bless you. I think that's it for the chapter. If you want to talk about any of these other questions at all, Sydney, anything? No?
Wait, did we finish number 7?
Yep.
What was it?
The possible angular momentum, magnetic, and electron spin quantum number. Well, it's an s orbital. So what is the angular momentum number for that? Quantum number. 0, right. So what's the possible magnetic quantum number? 0. And what about spin? Either I could have a plus 1/2 or minus 1/2. Because we give spin on electrons, we give them a value of, if they're spinning up, pointing up like that, we call that m sub s is equal to plus 1/2. That's just the number associated with that spin. And if it's spinning down, we call that minus 1/2. Sydney, you're laughing. Why? What's that?
I said I love this.
No, you don't. You guys hate this stuff.
I don't know how hard it is.
It's not hard, though. It's
I was just looking up there and just admiring all of it. It's artwork.
All right.
You're the smartest man we know. Yeah, you really are.
The bottom line. Listen, guys. When all is said and done. All right. No, you guys are not the worst AP class.
Are you sure about that?
I had an AP class that made me lose my temper, and I broke a yardstick over a desk. I've only been mad at school twice in 14 years. Once with that AP class that almost drove me out of teaching, and once when that one kid was making those racist comments. And but I was walking around. I probably shouldn't put this on. I'm going to pause this. I'm not going to tell the story online. Nothing bad, ladies and gentlemen, nothing bad. So the bottom line is, just picture it this way. Picture the box diagram. The box diagram will kind of give you a thing. Remember, n equal 1, I've got the 1 orbital, the 1s. I go up to the n equal, this is all you have to know. N equal 2. Well, then I've got the 2s orbital, and then I've got the 2p orbitals. And if you could remember, okay, just remember this. You must remember this. Okay, the s orbitals have 1 orbital in the set of s orbitals. So anytime, doesn't matter if it's a 3s, there's only 1 of them. The p orbitals have 3 in a set. And the d orbitals have 5 in a set.
So it's like a smaller animal can only eat so many. And then as you get a bigger animal, you can fit more food, right?
Well, I guess so. I guess that's not a bad analogy.
I mean, I'm just trying to make it so I can understand it.
S orbitals, there's only 1, and you can fit 2 electrons in. P orbitals, there are 3, and you can fit 6 electrons in. D orbitals, there are 5, and you can fit 10 electrons. And F orbitals, there are 7 in a set. That's all you have to know.
Just remember that picture.
Yeah, just remember that. And remember our remember our filling, our Aufbau principle, and the Hund's rule. And if you could do that, then I'm a happy guy. Okay. How do you guys feel about these electron transitions between levels and calculating wavelength, frequency?
I have the formulas, but I don't know all like the names of values, like the letters.
If I'm gonna be honest,
Yeah.
I'm lost.
Okay. All right. Let's take this time since it's parent teacher conference day and we don't have to start a new topic today, and I want to make sure you're prepared. By the way, where's Landon today?
Mac, wait for husband.
What's that? Oh,
It's like,
is he sick?
no, it's like,
Just slept in. I wish I could have slept in. I tried to stay up to watch the State of the Union address, and I fell asleep to it. Oh, talking about boring. Um. Anyway, all right. Did you watch it?
yeah, I was watching it.
I fell asleep right.
Yeah, I did too.
Yeah, it was boring. It was boring. They're always boring though. All right. So anyway, in summary of chapter 6, we learned about light. We learned about light having particle properties and wave properties. All right. We learned that light has a relationship between wavelength, frequency, and the speed of light. Okay. So if you know the wavelength and you know and you want to get the frequency, you can rearrange that equation to do so. Are you guys okay with going back and forth between frequency and wavelength? All right, good. We also learned that a quantum of light, a photon, has an energy of the energy of a photon is equal to hc over lambda, where h was just a constant. It's Planck's constant, and you should have that in your notes. And remember, your wavelength has to be in meters, and many times we see it in nanometers. Okay, so we learned that. And we also learned that this could be represented as h times frequency, and your energy is going to be in joules. We learned that the energy of one single photon is pretty small, but when we have moles of photons, you can have quite a bit of energy. We also talked about that energy, since it's inversely proportional to wavelength, the smaller the wavelength, the greater the energy of the photon. So for example, if I have some ultraviolet light, maybe about 300 nanometers or 280 nanometers or something like that, it's going to have a lot larger energy than red light at 700 nanometers. Frequency. Energy is directly proportional to frequency. The greater the frequency, the greater the energy. The greater the frequency, the smaller the wavelength. Because C over lambda is frequency. So as this gets smaller, that gets bigger. As this gets bigger, that gets smaller. Inverse proportionality. Okay, so that's our basic relationships for light. And when I say light, I can mean electromagnetic radiation of any wavelength. So then we talked about the various models of the atom. And we talked about the Bohr model of the atom, where we had these energy levels that got closer and closer to each other as we increased in energy. And we called this n equal 1, n equal 2, n equal 3, etc., etc., etc. And we said, hey, electrons can transfer between these energy levels, but they could only go between very, very discrete energy levels. You can't have an electron going from here to somewhere in between. They had to go just to these levels. So energy then is what we said was quantized. They could only take on certain values. Quantized. That means only certain values are available for these electrons. So we said, okay, if I excite my atom by maybe passing a lot of electricity through it or shining light on it, I can cause an electron to jump to a higher energy level, maybe the n equal 5 level. And this would be called the excited state because the electrons up here in a higher energy level. Down here, it's in the ground state. Now, if an electron drops down to a lower energy level, let's say it drops down to here, to the n equal 2 level, we said it's going to emit, and this is not to indicate that this is going to be a red photon. I just don't have any other pens here. So it's going to emit a photon. And we symbolize a photon, oftentimes we just write h nu. That means the energy of a photon. After we looked at this, we said, well, there's an equation that we can use to get the wavelength of that photon, or the energy. And that, we said, was called the Rydberg equation. And the Rydberg equation looked like this. 1 over lambda is equal to 1.097 times 10 to the 7 meters to the minus 1 times 1 over n lower squared minus 1 over n upper squared, where that lower and upper just means the upper is where I'm falling from and the lower is where I'm going down to.
Is that an M?
What's that?
Is that an M?
Meters to the minus 1, right. Because when you do a problem like this, you have to reciprocate that number so you can get the wavelength. We can get the difference between energy levels by multiplying both sides by h and c. Because hc over lambda is energy, and we'll call it delta energy, meaning the difference between energy levels. And that's going to be, I'm just going to call this constant r, so you know what it is, different than the gas constant. So h times c times r times this business right here. So you should be able to do a problem where I say, for example, if I give you a problem that an electron falls from the n equal 4 level to the n equal 2 level. What is the wavelength of the photon? All right, so we did that. And then we talked about electron configurations, going through the periodic table and looking at the electron configurations in the orbital diagrams, the diagonal rule. So I don't know, is there anything you want to see? You want to practice any of this? Everyone, now's your chance. I mean, I want you to at least understand the fundamental principles. Anna.
So if we're doing this on the calculator,
Mhm.
We have to plug all that in for R.
This? Yeah, let's do one. Let's say we're going to drop from the n equal 3 level to the n equal 1 level. Let's see what we get. So we're going to go, I have a photon. For some reason, it's in the, an electron. For some reason, it's the n equal 3 level, and it's going to drop down to the n equal 1 level, and it's going to emit a photon. So here we go. We've got our little equation right here. This is easy. The lower level is just 1. And 1 squared is just 1. And I drop down from the n equal 3 level, so 3 squared is 9. Now what you're going to do, what I do on my calculator is I do this part first and multiply it. So if I'm going to key this in on the calculator, I'm going to go, whatever this value is, it's 1 over 1, so it's just 1. So 1 minus, and then 1/9. And then I'm going to go ahead and multiply by times 1.097 EE7. And I come out with a number. And that number, see if Bryden can see this. Hope you're having fun in the sun. 975.1111 meters to the minus 1. It's important that you understand that unit. Now what we have to do is raise that to the minus 1 power. So I'm going to go my little caret here, -1, that's reciprocating it. You might have an x to the minus 1 button on your calculator. And I get a value of, my wavelength is 1.025 times 10 to the minus 7 meters. And if I convert that to nanometers, It's 102.5 nanometers. That's a pretty high energy photon. It's in the ultraviolet region of the spectrum. Ultraviolet means wavelength shorter than around 390, 400 nanometers. Infrared would be greater than 750 nanometers. Anna.
So you do that, the R constant
Mhm.
thing, and then you plug that whole thing in for R in the next equation.
Down here?
Yes.
Well, if you want to get the energy, you would. But
Oh,
but you could just take that number because it's in meters and multiply it by H and C. And that would give you the energy of that photon. Where go ahead.
so you don't have to plug in and lower that whole thing again?
Well,
After you already have
it
all-
depends. I mean, if you just want to get the energy straight out of the gate, then you can use this version of the formula. If you want to get the wavelength, then you'd use this formula. It's the same formula. This is just the energy version. So you'd get your wavelength, and then if you want to get the energy, you could just multiply that by Planck's constant and the speed of light. Right? Yes.
Will we need to have a constant Z for like charge?
No, we're only going to stick with hydrogen. Oh, and the other thing we talked about the de Broglie relationship. I forgot to mention that. And that was this. We said that if waves can be like particles, particles can be like waves. And we derived this equation, but I don't care that you derive it. The wavelength of a particle moving with a mass m and a velocity v is going to have a wavelength h over mv is the wavelength. Now, m times v is called momentum. And it's given the symbol p. So this can actually be written as lambda is equal to h over p. Just another shorthand notation for that. So you use this equation, and this is the kind of question I would give you on a quiz or a test. I would say, I have an alpha particle whose mass is, and I would give you the mass in kilograms. I have an alpha particle moving at 0.7 c. Remember, I told you that these are very high speeds these particles are moving, and we relate it to the speed of light. So if a particle is moving at 0.7 c, c is the speed of light, so it moves at 70% the speed of light, or 0.7 times 3.0 times 10 to the 8 meters per second. So it'd be like 2.1 times 10 to the 8 meters per second. And you just pop it in to the equation. So it's not that bad, not that bad. And this idea of understanding the orbitals, it's just something you kind of have to wrap your mind around. So, oh my gosh, it's almost time to go.
What are those last 2 units after? I can't remember that.
Which one? Meters per second. All right, guys, that's kind of a brief review. I think we can wrap this all up. Maybe I'll make you a mock test that you can go through for tomorrow, because I'm going to have plenty of time when no one comes to visit me on parent-teacher night. So,
We can go over it Friday,
and then we'll go over it Friday, and then we'll look forward to it. We'll look forward to a test next week.
like Tuesday.
My sister's coming.
Oh, I know. I emailed your mom. I told her to come around too. All right. There you go, Bryden. Enjoy.